Thanks for the warm introduction. And I'm very glad to be here to introduce our recent progress in quantum computing field. And first of all, I would thank our NIH for this special organization. And this is very wonderful event. So today, our speakers give very wonderful talks, not only from quantum computing, but also other topics like the data policy, data usage. And I also further thank the NIH last year, the Innovation Lab. Actually, we was honored for some of our research and at that time. And again, I will thank our lab members for this work, and also my collaborator, Fei Li from George Mason University. Okay, so this is definitely teamwork we trying to do. Okay, so before I go to some of details, I want to ask a question. So we have data. We want to do the data analysis for like bioinformatician and biologist. So if you have two options, one, so you want to get the best solution, but take 1 month. Another option, so one day.
Apologies, there's a technical issue. Just give me a second.
Oh,
sorry.
All right.
Let me just.
Cool. Thank you. Okay, so another option is you can get some solution in one day, but it's not the best one, probably just approximation. So which option you would like to choose? The first one or the second one? The first one, raise your hand. The best solution for 1 month. Okay, all right. So the second option is in one day, you get some approximation. What do you want? Do you want the second one? Okay, yeah, okay, cool. I think like it seems like a more, like our scientists choice the second option. So the time is important. Yeah, okay. So, however, yeah, the time is very critical based on our theory, like right now, like based on the Turing machine. So far, all our like the computational models, 99% of them like based on the Turing machines, definition. So like the NP hard, the incompleteness. Okay, so that means for many of those questions, if they are NP hard, NP complete, you can't suppose get the polynomial time algorithms to resolve those questions. Yeah. In that case, we give up. We want to get, like the approximation. Okay. Whenever it's not the best, give me something. So the thing happened in the last many tens of years so far. Yeah. So quantum computing, it seems like open a new window and a totally different computing model compare with the Turing machine model. And like Feng introduced in the previously, like there's use of different mechanisms to calculate, to model, yeah, this, like the NP-hard questions. All right, so it seems like the quantum computing can have some of like the superiority in resolving those. And how do it? and what if we expect to apply them in like our like bio data analysis. Okay. I want to here just use very simple and plain language to tell you like one simple example, like the clustering question. So everybody knows cluster question is widely used in data analysis. Many of cases like single cell or mixed data analysis, this clustering probably almost the first step to get something biologically. Yeah. So, but you know, like the clustering question, by the definition, formally, actually in math, we also know it's NP-hard question. Yeah. So, like you may know, like the k-means, concentroid, like the clustering methods. Actually, they are NP-hard questions. We use those k-means algorithms or something. It's just a heuristic algorithm. There are no guarantee. You get the best solution. And most of the cases, the reproducibility is another question. Yeah. For example, the k-means, when you do the k-means, if you use the different seed, random seed, you get different result. Yeah. So, but we used to, yeah, we have no other choice. Yeah. So we hope like the quantum computing can, you know, help us to escape those constraints. Okay. Just a little bit formally, like introduce like the clustering here is like if you have a set of objects, you want to cluster them into several subclusters. Okay. So from quantum computing of this, you know, like the techniques or series, we can go back to more than 40 years ago. And so there's, as introduced, like the Shor and the Groove, they have like two very fundamental and big through of these algorithms. After 2020, so the quantum computer have you know, like speed up like for more and more qubits available, and to allow us to do like to resolve a more large scale of those questions. Okay. Okay, so let's go back to the cluster itself. All right, so like the k-means, mainly there's the clustering that have the two types of those ideas, like the center-based or like density-based. Those algorithms either like use the random seed, use the arbitrarily defined the center, or use or like they are sensitive to the outer layers. So what we did is like you know, like we first introduced a new algorithm, it's non-centralized methods algorithm to do the clustering. So this is based on the class called like the convex analysis in math. So we want to use it based on this, like, okay, so how can we get to the best solution? Okay, so eventually the idea is, from this figure you can see we want to cluster those nodes in different of those clusters that use the different colors. Yeah. I want to draw your attention here is like this one. This node actually is outlier to, if you think like to the other clusters. From this real data from Professor Yong Chen's lab, so they provided, so they clearly annotated the first, the yellow cluster, actually they are digotic cells. Yeah. And there's the 2 cell and the 4 cells. However, you can see this is, if just by iris, it seems like they are pretty close to the 2 cell stage. Yeah. If you use the k-means and other centralized methods, you can easily cluster this node to the other clusters. So based on our methods, we use the so-called the k-value methods, like to do the clustering. So those non-centralized, methods can correctly actually cluster this node to the Degotic cluster. Okay. All right, so this is a brief summary of those algorithms and the anti-hard questions for this K-center, K-media, K-means. Yeah, so, all right, so for this cluster analysis, the quantum, the efforts in quantum computing also started. Yeah. So, however, there's several of this, the algorithm, again, so they are just sometimes just very briefly and quantumize this one or two steps of those, algorithm. Yeah. Again, so that means it doesn't resolve exactly the algorithm itself. How can we get the best solution? Not just like, okay, yeah. That means when we design quantum algorithm, this is very, very key challenge is how you model or operate your model your question with the hardware, like the qubit. Yeah, so that is the key points. Okay. All right, so for our methods, the idea actually is just like that. So we want to use the different of the first you use the convex the whole concept like to partition those the clusters the nodes into subclusters. Here this is our previous the classical one, classical pseudocode. So here I want to introduce how we do this in quantum version. Okay, so to do this quantum version, actually, it's not just directly translate the classical algorithm into quantum version. We de novo design this algorithm. Okay, this de novo design actually is based on here we trying to model or transform is like the qubit version to resolve it. Okay. So here is the function we want to max, we want to calculate. Yeah. So here, actually, we want to maximize the total removed area, because we want to partition these nodes into subgroups, and then so we actually that means we want to remove, the space between them, those subgroups. And so we can maximize those volumes among them, those those subclusters. Those subclusters also modeled as like the convex halls. Okay. So here we first do some of data proposition. Like first one, we can, to project or use the dimension reduction into small, or lower dimensions. For example, we can into this and construct the first convex hall like that. And then, so we do the triangulation. Okay, so to show it, each of these, the triangles have this, the areas sizes. Yeah, this here I use this like a two-dimension data, for example. Yeah. Then, so the core part of the algorithm is trying to, remove the area within this, the big convex hall into small, convex halls, by remove the space between them, among them. Okay. Technically, we first label all those nodes into different of the colors, like two colors, the red and black. And so during those, the remove, to remove them, which triangle should be removed and how get the best solution. So we give them the binary code, 1, 0, and 1. Yeah, that's briefly the idea. And then, so the key point here is you need to well design and your operation this table like this, like at which case, if there's a 0, 1, 0, 1, 1, 0, so which case you get like the operation, and then so input all those operations into your function and construct the Hamilton, like the system to either like a D-wave annealing computer and to resolve this. Okay. All right, so I skipped some of the details of those, like how we formulate those, the ones. Mainly, we want to, like maintain during the searching process. We want to maintain two properties. One is the convexity, and another one is continuity. Okay, so make the searches the process correctly, like performed. Write those code in QSCADE, and so you can run them like by like here, probably it's quite small, like but we publicly released it from GitHub, so you can like run this toy example. Yeah, here I give these two figures just to showcase. Okay, if we technically, if you just keep the convexity but not maintaining the continuity, so you will get left. But if you keep both, so theoretically we proved, so you can get like this partition correctly. Yeah. All right. So this is just a small example. I want to show you like how we design those. Like that means when you design a quantum algorithm, it's not just like, again, not just like, okay, I have a classical one, I just translate into a quantum version. Actually, those algorithms, based on your question, you define your math question, you need to, like communicate with the quantum computer. And unfortunately, actually, so far, the quantum computers have different techniques. Yeah, annealing-based, gate-based from IBM, from other like quantum computers. So they use different of the techniques. That means you need to write different of the code to perform your like the algorithms. Okay. For brief summary, okay, so we de novo designed a quantum clustering, algorithm for those data analysis, for single cell data analysis. We, during this, like the algorithm design, actually our broad, like a broad view of this, application of quantum computing in bio data analysis is, okay, quantum computing is so far is also a very big field, like many of those theoretical studies, hardware studies. But what we can do for biomedical data analysis. So we focus on some of those questions, okay, like the clustering, like the single cell data analysis, like to resolve the ODEs, PDEs for this system levels simulations. Okay. And another one, like we proposed in the innovation lab. So we also interested about like to conduct like those, to resolve those NP-hard questions for network optimization. Yeah, because network optimization actually is widely used to simulate the biological, like network. Okay, so I also want to discuss with you some of limitations so far. Yeah, limited access of quantum computers. Okay, so months ago, D-Wave is free. You can, have a free access time like to run your program there. But so far, right now, they ask for money. Typically, per minute, $100. It's pretty expensive. At least I think it's expensive. Yeah, yeah. so far also like the total numbers of qubits is still limited. I mean, we already scaled up to like thousands of levels, but it's much, like far from, like sufficient for large scale data analysis. Yeah. All right, so, but anyway, I think like the quantum computing is very promising field, like especially to study modeling complex biological phenomena or questions. Yeah. So because like for example, if we want to model the whole cell levels, those reactions and the different of those, like molecules, gene transcript regulations at the molecular level. So it definitely is quite large scale. Yeah. So how I think like with the development of the quantum computers, this is the next promising way. Definitely go back to the major advantage. Again, quantum computing provide a theoretical possibility compared with Turing machine for resolving these NP-hard questions. Yeah. So that's me. You can expect someday you can get the best solution in reasonable time. And not right now, like probably take months and years like that. All right, I will stop here and leave the time for any of the questions.
Thank you, Dr. Chen, for sharing. So for sharing your unpublished result with the audience. And I'm happy to see you are sharing the code. So, and for one of the fundamental problem, clustering. So if you are doing bioinformatics, clustering is one of the fundamental algorithm, many of them. So for fundamental program, it is extremely hard to make any improvement. That's my understanding. I'm happy to say Dr. Chen is trying to make improvement. So time for one question.
Thank you for the very nice talk. It was very nice to see the improvements being made in the triangulation. I'm wondering whether or not you think that this could also be useful for biological problems in surface reconstruction. So for instance, in radiology, a huge amount of GPU hours are spent trying to reconstruct surfaces from point clouds taken during MRI or CAT scans or things like that. Where it's another problem that's unsupervised, trying to figure out how to learn meshes or other flat surfaces to define boundaries.
All right, thanks for your question. I think there's a very good question about this idea. Basically, this idea I believe can be extended to very broad like applications. Before during our, like the algorithm design, I frequently discuss with my collaborator, Dr. Fei Li. So go back to, go back to 20 years ago. So when I was like a PhD, I work on like the operational research, like those, optimization theory. And so I think like, those ideas fundamentally can be, like linked to go back to like a convex analysis and go to like to improve the classical optimization theory, like the integral point algorithm and the branch and bound algorithm. So those ideas like it definitely is quite broad. Not only can be used for like those, clustering, but also like the machine learning, most of the machine learning models, the loss function we define is like the quadratic, like functions, because in operational research, the quadratic, programming is well resolved in polynomial time. However, like the non-convex case, and also like even let's go back a little bit, like the DC programming, like the difference of two convex program, like still, like resolvable, but it's quite hard, like use the branch bound. Branch bound is like a smart way to enumerate all possibles. So it's quite suitable, like the quantum mechanism to do that. So anyway, so I would like to see, Yeah, that's a very good like direction. So we definitely, you know, like interested to contribute not only from like the QBall based the solution technique, you know, roadmap, but can we also expand the classical algorithm like the optimization theory in quantum field, like to resolve like, you know, like the more general and broad, you know, like the questions. Yeah, thank you.
Thank you, Dr. Chen. This concluded all of our scientific presentations.